Hello. Okay, so I'm going to go over each question of the homework and just kind of tell you my thought process, or the classwork, sorry, and tell you my thought process behind each question. So number one is the one about the fish. It tells us we've got these 8 tanks, they're in this room, the north side is colder. And we want to describe a design for the experiment that takes into account of the temperature gradient. So taking account of the temperature gradient means we're going to include blocking. Blocking in an experiment means we are separating our group of subjects. In this case, our subjects are each tank based on some similar characteristic that we think is impacting the end result. So in this case, we think that the placement in the room, the side of the room that it's on, is impacting the end result because one side is colder than the other. So I'm going to first say that I'm blocking by side of room. When I'm describing an experiment, the first thing is I need to make sure I'm specific about the randomization process. That would include numbering. In this case, the tanks are already numbered, but that also includes the method that we use to choose which numbers go to which treatment. We could use that by flipping a coin. We could do that by assigning numbers. Like I said, in this case, they're already numbered, and then using a random number generator or picking numbers out of a hat or whatever. We just want to make sure we're specific. Talking about random number generator is generally the easiest way to describe that, but you do have options. To describe that really quickly, here notice that I did use the word unique. That is really important because that makes sure that we have 2 different tanks from the north side and 2 different tanks from the south side who are getting one of the treatments. You could also say like without replacement, and that would kind of cover the same thing. Notice also that I kind of did the randomization process for both blocks at the same time. Again, that was really easy because they were already numbered, but you can kind of run into that option. It just kind of depends on what the details of the problem are and if it's easy to do it that way or not. Okay, the second part of an experimental design after the numbering process is that I want to make sure and explain what each treatment is and like who or what objects gets which treatment. So I'm going to say that part. And I'm actually going to change this a little bit. I'm going to say the salmon in the tanks whose numbers we've chosen will be given the new, and the salmon in the remaining tanks. It's always a good idea to be as specific as possible. Really important here, you wouldn't want to say the numbers who were chosen will be given the new food because numbers don't eat food. Salmon eat food, but numbers don't. So those are kind of little picky things that aren't going to give you full credit off on a question like this, but you would kind of be knocked down from like full credit to like partial. So just be really careful for things like that. Just be detailed and think about like, does this logically make sense? So I've described what the treatments are. It's also a good idea to include the word treatment somewhere in there. Again, it's not a huge thing, and if you had everything else perfect, they probably wouldn't knock you off for that, but it is something to be aware of. Using the word treatment kind of shows that you understand what an experiment is. And then the last thing we want to make sure and mention in an experiment is we want to say what we're going to compare at the end after the treatments have been done. So this one, it said there's 6 months involved here. So I'm going to say after 6 months. And then say what we're going to compare. In this case, it settles up here, we're comparing the weight gain of the salmons. All right, so we can compare kind of within each block, but also overall. I might say that. I don't know if it's necessary, but again, doesn't hurt to be more specific. And that is it. That's your kind of question on this one. This one's a really short one, just had one part. When you have questions like this, know that each free response question as a whole is going to be worth the same amount of points. So one like this that only has one part, those are ones that you really want to be super detailed on because that means the whole amount of points is being divided just in this one part. So the more specific you are, the better. So that is number 1. We're going to now move on to number 2. So number 2 is one that's kind of weird. I threw this one in the classwork because there is a little bit dealing with this unit. We've got a little bit about bias on part B, but other than that, we're kind of pulling in stuff from confidence intervals. We're pulling in stuff from just basic kind of probability and dividing numbers. So this is a kind of question you'll see sometimes. Free response questions usually aren't completely on one particular unit or type of question. There's going to be a lot of stuff that's mixed. So I want to give you some practice with those types of problems as well. So on part A, it gave us up here the interval, the 95% confidence interval for the proportion of all students who would respond yes was calculated as 0.584 to 0.816, and then it just says how many students were in the sample. And I remember when I did this question a few years ago on a practice test, people were completely thrown off. How am I supposed to know that? Am I supposed to guess? But you have an interval, You are told that it's a 95% confidence interval. That is actually enough. What we're doing here is kind of working backwards and knowing the equation for a confidence interval and knowing what gets plugged in where. So I'm going to be typing this out this time because that's what I'm doing. Normally I would write this out for you. We're kind of doing some algebra. The first thing that I would do is this interval is the whole interval. If I wanted to know what the actual proportion she got from her sample was, that sample proportion is always going to be in the exact middle of the interval. So the very first thing that I would do is figure out what my point estimate is, or sample proportion, that she got from this set of data, and that would be just figuring out what is the exact middle, so just kind of averaging them. So averaging 0.584 and 0.816 gives me 0.7. So I can figure that out just by averaging the two numbers. So I know that. That is my p hat, that is my sample proportion that I'm using in my interval equation. The next thing I might want to do is figure out what my margin of error is, and I can figure that out just by looking at margin. 0.7 is in the middle, so what did we add to 0.7 to get the upper part of the interval? What did we subtract from 0.7 to get the lower part of the interval? So just do a little bit of subtraction. I'm going to do 0.816 minus 0.7, which gives me 0.116. So we know that the margin of error is 0.116. So from there, what I can do is set up a margin of error formula. We did this a lot with types of questions where it's like, what should my sample size be if I want to guarantee this margin of error? So it's kind of that type of question. In this case, I know what the margin of error is in the interval, and I'm working backwards to figure out what the sample size was. So I'm going to go ahead and say my margin of error is 0.116 equals. Margin of error formula for a confidence interval, we start with our critical value, or z star. So if I know I had a 95% confidence interval, I know my z star for that is 1.96. And then we have times the standard deviation or standard error of the statistic, which our formula for that for a proportions problem is square root of p times 1 minus p over n. So we know that our p, or sample proportion, is what we would put in there for a confidence interval problem, is 0.7. Right? That was the first thing we figured out. So 1 minus p would be 0.3. And then n is what we're solving for. So now we've got this equation. We're going to do some algebra. So I'm going to start by dividing 0.116 by 1.96. And I get 0.059-ish. I'm going to type this out, but I'm not going to clear that out of my calculator because I don't want to round. So now I have that. Right, so the next thing I'm going to do is square both sides to get rid of the square root. So in my calculator, I'm just doing that last number squared, which gives me about 0.0035 equals, and then 0.7 times 0.3, I'm going to go ahead and say is 0.21 divided by n. I did that in my head. And then the last thing would be to multiply by n, right? So 0.0035 times n equals 0.21. And now I can do 0.21 divided by n, and that would give me 0.21 divided by, not by n, sorry, 0.21 divided by that 0.0035 number. Again, I'm using what was in my calculator and not rounding, and I get n is 59.95, so about 60 students was what she sampled. So again, I was really just working backwards from what I had. Seems like it would be more complicated, but it really is just figuring out what I know and plugging it into my margin of error equation. Right? So part B is where we're actually getting into a little bit of the stuff from this unit. So it's saying that the method used by the environmental science teacher, she says up here that she basically calls them into her office and asks them, do you regularly recycle? So she's asking them face to face. This would be an example of response bias. When you're writing this out, it's not as important that you include the type of bias by name. It's more important that you describe it. So we are going to describe, what does that mean? Well, in this case, she's asking them face to face. She's the environmental science teacher, and probably most of the students know that. And they wouldn't want to say, no, I don't recycle, to the environmental science teacher. They want to impress her or look good to her, or at the very least don't want to kind of get her mad at them and don't want to get into a whole big thing. So then probably these students are more likely to say yes. And that brings me to the other part. Anytime we're describing bias, we want to make sure and mention a direction. So don't just say it's different from what it would be for the whole population, or her estimate is off, or it's not representative. We want to say specifically which direction. So is that point estimate or that sample proportion, is it too high or too low based on that type of bias. Part C is very long, but it's actually a lot simpler than it looks. So part C is saying that she's trying to avoid that response bias that was an issue. She's still going to ask them face to face, but she's basically giving the kids an out. So she's going to tell them to privately flip a fair coin. If they flip heads, then they must respond no, regardless of what their true answer is. And if they flip tails, they can answer truthfully. So that gives students an out. She's not going to see what they flip. So if they say no, she doesn't know if it's because they flipped heads or if it's because they truly don't. My hint to you on this was to kind of don't make it harder than it is. So for part I here, it says, what is the expected number of students from the sample of 300 who would be required to respond no because the coin flip resulted in heads? So we're really just thinking basically here. What would we expect? What percent of the time do we expect to flip heads? Would be 50% of the time. So I'm going to say 50% of 300, about 150. So approximately 150 of the students would be required to say no because they flipped a heads. So for part 2, it says that the sample showed that 213 responded no. Based on the results of the sample, give a point estimate for the proportion of all students who would respond yes. So 213 responded no. What we're going to do here is basically take out that approximately 150 students who were required to say no and just ignore them completely because they were obviously required to say no. So we're really only going to be looking at 150 students. So I'm going to say 213 no's minus 150 required no's would give me 63 truthful no's. So that would mean 87 truthful yeses, right? So then what we can do to figure out what is the point estimate, what is the sample proportion for the true amount of students who would say yes. So I'm going to say 87 out of 150 is about 0.58. Okay. So the about 58% of the sample would truthfully say yes. So 0.58 is our point estimate for the proportion of all students. On to number 3. So number 3 is the question about the deer. They want to use a method of figuring out how many deer are in the region, but they want to make sure they're including all parts of the region so they get a good estimate. They're going to randomly place 90 salt licks throughout the region, and then it tells us there are 3 main areas: the forest, the town, and the lake. So A says 2 methods have been proposed for choosing a simple random sample or stratified. So when they choose which spots they're going to put these salt licks in, they're going to do it either as a simple random sample. So that would mean they kind of look at what are all the possible places that I could put it. Maybe there's 500 possible places in the entire region that they could put a salt lick. They're going to pick 90 of them, either with a simple random sample or as a stratified. So just as a quick review, stratified is where we group our possible subjects, in this case possible places to put a salt lick, by some common characteristic that we think has an effect, in this case the area that it's in, and then pick a sample from each strata, from each group. As a reminder, when you are comparing 2 options, you always want to make sure and mention both. So mention why stratified is a good idea, but also why simple random sample would be a bad idea. So stratified would be good because that would mean I'm placing salt licks for sure in the town and the forest and the lake. And that means that I'm getting a better representation from each area. That might be important because probably there's not as many deer that are hanging around town than compared to like the forest or the lake. So if I do a stratified random sample, I'm guaranteed to get some data from the town and from the forest and from the lake. Whereas a simple random sample, it's possible that I could pick 90 locations to put salt licks that are all in the town. And then I would think that there's not very many deer in this region because all of my salt licks are placed in town. Or I could pick 90 locations that are all in the forest, and then I might think that there are tons of deer in this region because all the deer are hanging out in the forest, and that's where I put my salt licks. So by placing them for sure in each region, I'm getting a better representation of what's true about the entire region. So I'm going to say something to that effect down here. I talked about why stratified was good. I talked about what could go wrong with a simple random sample, and that kind of tells me why stratified is a better idea in this case. Part B is saying that the hair snare method are sampled with replacement. The reason for that is if they're just kind of collecting hair from any deer that comes up to the salt lick, there's nothing that's stopping the deer from going multiple times to a salt lick. So they get 20 hairs off a single salt lick. Well, that could be 20 different deer, or it could be the same deer 20 times, and they don't really know which is which. Make them estimate that there are way more deer than there actually are, when really it's just fewer deer that are going to the salt lick multiple times. Notice that I again mentioned direction. This problem could make the estimate of the number of deer higher than it actually is. So they think that there are more deer than there actually are. Just to cover my butt, I'm also going to talk for a minute about how without replacement would be a better method and what that could do. All right, so that is number 3. So moving on to number 4. Number 4 says that talking about people with fear of heights, sometimes enroll in therapy sessions. Study was conducted to determine whether D-cycloserine used in combination with fewer therapy sessions would help people with acrophobia overcome their fear. So it says that 27 people, 17 received a D-cycloserine pill, and the remaining 10 received placebo. It says they were randomly assigned. They had 2 therapy sessions, and then none of them received additional pills or therapy. 3 months after, they evaluated the people again to see if they had improved. Part A. So in this case, because they told us up there that the 17 of the 27 were randomly assigned, we know it's an experiment. So I'm going to say this is an experiment because they were randomly assigned, whereas if they were allowed to choose their treatments, then it would have been an observational study. Part B says that the D-cycloserine group showed statistically more improvement than the placebo group. Based on this result, would the researchers be justified in concluding that the pill, this D-cycloserine pill, in 2 therapy sessions are as beneficial as 8 therapy sessions without the pill? So we have to be careful here. Yes, we saw a difference, statistically significant difference between the 2 groups, and because there was random assignment, we are allowed to show cause. But we're only allowed to talk about causation in relation to our actual 2 treatments. This question is pulling in this 8 therapy sessions thing. That was not one of our treatments. We cannot say anything about 8 therapy sessions without a pill if that was not actually in our experiment. So the answer here is no. Okay, so we cannot say any kind of conclusion regarding that specific thing because we didn't actually test that in our experiment. Now I am going to add on that we can say that D-cycloserine causes better improvement compared to a placebo because that's what we actually tested. We can say that D-cycloserine causes more improvement compared to placebo because those are the treatments we tested. There was a significant difference and the treatments were randomly assigned. All right, and then part C, the study or the article just talked about the 2 different treatments. They didn't specifically say how it was determined who got what. So suppose that researchers allowed the therapist to choose which people received D-cycloserine and which received the placebo. No randomization was used. Explain why such a method of assignment might lead to an incorrect conclusion. So by eliminating the randomization, we are dealing with more variables that aren't being controlled. So randomization in an experiment is kind of what is controlling any other variables that might be affecting people's improvement. So we know that some people improve better than others just based on who they have as a therapist, or it could be the location that they live in. It could be how willing they are to get better, how much they believe in medication, etc., etc. So when we randomize, we are kind of splitting all of those variables amongst the 2 groups so that it shouldn't be affecting the final conclusion, whereas if we let the therapist choose, then those other variables are still very much a part of the problem. So I'm going to say it's something to that effect. So without randomization, any other variables are not being controlled, and any of those variables could actually be the true cause of the improvement. So we wouldn't know for sure whether D-cycloserine was helping or if it just happened to be that those people whose therapist gave them D-cycloserine, who believed in the effectiveness of the treatment and maybe thus treated their patients better, and that was the real cause of the improvement. So we want to make sure and talk about those other variables, maybe mention what those other variables might be, but then just kind of mention that without that randomization, those variables aren't being controlled, and that's going to lead us to thinking that the medicine works when it may not actually be the medicine. So that is the end of number 4, and that is our first assignment for this week. If you have any questions about any of those problems or just questions in general, feel free to email me or send me a remind text, or you can do a message in Google Classroom. Lots of options. But anyways, let me know if you have any questions. Have a good week. Bye.